Okay. All right. So, welcome everyone to the 54th episode of the SFU Sports Analytics Virtual Seminar Series. Today we have Dr. Ali Hassanzadeh, who's going to speak to us about fairness, tanking, and competition design in professional sport. Uh, Ali is a lecturer, equivalent to an assistant professor here in North America in management science at Alliance Manchester Business School at the University of Manchester in the UK. He holds a PhD in operations research from the University of California at Irvine and works at the intersection of optimization and data analytics. He studies fairness, scheduling, drafts, and competitive balance in professional sports leagues, including basketball, cricket, and football. He has published in journals such as Manufacturing and Service Operations Management and Transportation Research Part B methodological, and collaborates with academics and industry partners on data-driven sports analytics. Just trying to advance the slide here. There we go. Okay, so in terms of a summary of this talk, professional sports leagues make many structural decisions that strongly influence what fans see on the field, how schedules are built, how drafts allocate talent, the games that are selected for broadcast, and how competitive balance is maintained. In this talk, Dr. Hassanzadeh will present questions and results from sports that study decisions using analytics and optimization, such as basketball, cricket, football, and tennis. Dr. Hassanzadeh will discuss how scheduling algorithms affect fairness and competitive balance, how tanking and draft incentives shape team behavior, and how strength of schedule can distort performance evaluation. The talk draws on published work as well as ongoing research on NBA expansion, draft design, cricket competitiveness, and football scheduling. Throughout, Dr. Hassanzadeh will focus on intuition, real-world implications, and how relatively simple models can answer important questions in sport decision making. So with that, thank you again for joining us, and I'm going to let you share your screen, and we look forward to your talk.
Thanks, Dave. Appreciate it. So let me try to share my screen. Uh, so it says someone else is sharing, so I'm gonna send a request
Oh,
to
sorry.
share my screen.
Yeah, mine didn't turn off properly.
All right. So hopefully you can see the screen all right.
Yep, looks great on my end.
Okay. Okay, thanks, Dave, for the invitation. Um, I actually visited Vancouver this summer, um, and I had a talk at the BD School of Business. I only met Tim Schwartz from the sports analytics group. I knew Tim before. He didn't know me, but and then he introduced me to Peter White, and then I got introduced to Dave as a result. So that was a story of, me connecting with your group, which is an amazing group. I've been keeping an eye on the website, publications, and activities. And I'm hoping that someday we can also build a sports analytics group in our university. And that's actually what we're aiming for, trying to recruit more people working in the intersection of analytics and sports. Um, so this talk will be based on a few studies published and also a few ongoing research um, uh, which I'm doing myself as a researcher, some PhD students, some colleagues in other universities and other countries that I'm going to talk about. But essentially, it will cover in terms of sports. I don't think I will get to all of the slides that I have available in 45 minutes. I'll see what I can do. Probably I will have to skip through some slides, some details. But basketball, football, and cricket has been basically mostly what I've done. And it really started from basketball when I was a PhD student in Irvine, Southern California, and especially during COVID when games stopped and lots of interesting problems, started floating around in my mind. And then that was the beginning of me basically being involved in sports type problems. In terms of problems, scheduling and sports league, which is mathematically, as you can imagine, it's a very difficult problem. Um, especially in North America, given the competition format, it's actually very difficult to come up with a new schedule that makes everybody happy. Competition design, player performance. This is more related to my work with cricket and our work with English and Wales Cricket Board here in the UK, and then player drafting. So that's on NBA draft, which I'm doing with a few master students right now. And we don't even have any results, so just starting. And I will hopefully I'll have time to basically at least tell you what the research question is. And then in terms of tools, optimization, machine learning, simulation, and so that's what I do, what I know by training, and what I use. In terms of leagues that these problems and tools are focusing on, MBA. Um, so the problems that I studied in the MBA generally applies to other three major sports leagues in North America: hockey, American football, and baseball as well. But I have mostly used the NBA data to test anything that we've done. IPL, which stands for Indian Premier League, that's the cricket league. The T20 format, which was started around 2008. English Premier League, which is a representative from double round robin football tournaments or soccer tournaments around the world. And then women's tennis, which in particular has drawn my attention because of the differences in the format, and I have basically come up with some fairness related questions related to women's tennis that hopefully I can talk about. So the first paper really was the first one that got me interested in sports related work. So I'm an industrial engineer by training. Um, Optimization is the main tool that I know, and I've been doing that for 10 plus years. And this is also an example of using an optimization problem to answer a decision problem. Um, and this is published at MSOM. You can have a look. And also, this is a joint work with my supervisor, John Turner, and my colleague Mojtaba, who's now at Iowa. The story started really in March 11, 2020, when the NBA suspended games, and there was a lot of speculation as to how the NBA should conclude 2019-2020 season. And one of the alternatives was to because if you recall, it took NBA 4.5 months to actually resume the league, and by that time, they didn't want to delay the next season, and they already had limited time to conclude the current season, so they wanted to conclude the season using a subset of the remaining games. So the playing out the entire set of remaining games was not feasible. Now the question that I focused on was, okay, so which subset of the remaining games should we play and which games should we cancel so that the resulting outcome is basically as reasonable as possible. And I will try to define what reasonable means here. I'm sure I do this introduction in Europe because nobody's familiar with basketball, but hopefully in Vancouver, you guys are familiar with NBA. But just to say a few words, we have 30 teams. Roughly, we are playing around one game every 2.2 days, which is very compact schedule. From mid-October to mid-April, 82 games per team. It's an asymmetrical round robin tournament, which means the number of matchups between any pair of teams depends on their geographical and divisional affiliations, two, three, four, in some instances, 5 games. So that's the format. And so at the end of the regular season, the season doesn't end there. Contrary to, for example, football or soccer leagues that at the end of the regular season, that's it. The number one ranked team becomes a champion. But in the case of NBA, we now have playoffs at the end of the season. top 8 teams from each conference advance to the playoffs. Top 4 teams have home court advantage. Draft picks are also important. So at the bottom of the ranking, there's also competition who gets the best draft. It's been a long time since the draft position is tied to a lottery system. So it's not deterministic in the sense that team number 30 gets the number one draft. Used to be like that, I think 40 plus years ago. Um, but all in all, this slide tells us that rankings are important. And if we want to address that, concluding a shortened season question, probably we need to have an objective function that is tied to rankings in one way. And we've had some instances of suspensions in NBA and other three major sports leagues. And in some instances, actually, the suspension was significant in time. The league had to cut a few number of games, which, we call that shortened season. Whether in the middle of the season or at the beginning of the season. So we've had some shortened season instances in other sports leagues as well. This actually didn't appear eventually in the paper, but I thought it's an interesting side note that I can bring to your attention. So in the review process, which was very long, it took us 3.5 years. Um, so one of the reviewers asked us if we can find evidence of tanking. And then I thought, okay, so we can look at some metrics that we can actually assess the performance of individual players by looking at their individual stats, positive stats, points, rebounds, assists, etc. And then on the other side, personal fouls, turnovers, etc. So there's a simple efficiency rating that adds all of these, um, stats together and divided by the number of games per player gives us a number which is roughly between 0 and 35. In history of basketball, very rarely a player scores above 30. So let's say only Michael Jordan and LeBron James and those caliber players score above 30 on average. So by definition, the league average player is around 15. And I looked at individual teams, and those teams that eventually didn't make it to the playoffs, bottom 14, let's say, of the league. And then I focused on their top three players. And then this graph basically visualizes the average of those top three players in terms of the efficiency rating. So what we are trying to understand here is whether there's a drop in top three in non-playoff teams, which means um, teams don't want to play their best options, right? So they bench their top players, and really that was the only evidence of tanking that I could come up with because even if you bench your players, if you look at the results, the win or loss, players are competitive and coaches are competitive. Nobody wants to lose except maybe organizations, right? Um, anyway, so that was a side note that I wanted to uh, mention. So back to the story of this paper. Um, so now we have four alternatives, let's say, to conclude the season, which is suspended or disrupted in the middle of the season. Number one, regular season playoffs are canceled altogether. There was even, I mean, I was a huge NBA fan. I still am, and I was listening to lots of podcasts, and there was even discussion around asking from experts and voting for a champion from the list of teams that performed really well before the suspension in COVID year. And second one, the NBA directly moves to the playoffs, canceling the remaining regular season games. So as you can imagine, this might not be the fairest compromise because certain teams might have had difficult or easy schedules leading to the suspension, and similarly on the remainder of the seasons, some teams have had easy and some teams have had difficult schedules. So giving teams at least a few games chance of improving their rankings could be basically a better option. Number three, no cancellations. All the remaining games are scheduled to play. Again, this is in an ideal world if we have enough time and there's no logistical challenges. This could be the best option, the fairest option, because the full season is agreed among everybody. That's fairest possible solution. But it wasn't possible in the COVID year because of timing issue. They wanted to limit the number of games. There was already concern around contracting virus, etc. That's why they came up with the fourth option, selecting a subset of the remaining games. So in that particular year, there was 259 games remaining, and the question was, okay, so can we select half of these games to play? So we call that shortened season here. And as you can imagine, shortened season while canceling certain games, the resulting ranking might be a little bit different than a full season ranking when we play all the remaining games. Now, our goal is to select these shortened season games in a way that these two rankings is as close as possible. So that's basically our objective here. We want to close the gap between these two rankings. We want to define some notion of similarity or dissimilarity to minimize or maximize between these two rankings. But the difficulty here was that these two rankings depend on some unknown match outcomes. So the resulting ranking at the end of the full season or shortened season depends on the outcome of the remaining games, and we don't know the outcome of the remaining games. We can only predict them. We can only estimate them, right? So that was a challenge, and so if I want to explain the metric that we use very briefly, um, and I'm going to use this very simple uh, toy example. Let's say we have four teams in the league and we have two alternative rankings, and I want to define some similarity or dissimilarity metrics to study how what's the difference between these two rankings, one and two. Based on the literature, Kendall's tau, or we call it concordance, is one metric that we can use, and that looks at pairs of teams. And if the relative position of those two teams in each pair is the same in two rankings, we call that a concordant pair. For example, in this small example, Los Angeles Lakers and Boston, in both rankings, Los Angeles ranked higher than Boston. So we call Los Angeles Lakers and Boston a concordant pair because both rankings agree in the relative position of these two teams. Whereas if you look at Boston and Milwaukee, Boston is ranked higher in ranking one, whereas Milwaukee is ranked higher in ranking two. So those are discordant pairs. If we assume that the number of concordant and discordant pairs add up to total number of pairs of teams, so we can just focus on the number of concordant pairs between the two rankings, and that could be our objective function in our optimization model that we want to maximize. Another alternative, which is slightly simpler, is simply just look at the Euclidean distance. Take the difference between rank number in ranking one and two for each team, and square them and add them all up, and then that's basically this squared Euclidean distance, so we don't take the square root. Um, and we have some theoretical result in the paper that shows some inequalities between the two, and we need to use both of them for the reasons that we have elaborated in the paper. And so if so in the NBA season we have 82 games for each team, But if we look at calendar days, we have games starting from mid-October all the way to mid-April. And in terms of the number of days, we have around 170 or 175-ish. So let's say 180. And then in this graph, on the left-hand side, we have concordance, and on the right-hand side, we have Euclidean distance. And we look at the distance between the ranking on each calendar day and how different that is uh, with the compared to the end of the season ranking. And that is studied and calculated in the past for not past, but in 14 NBA seasons from 2004 till 2018 that we tested as our like problem instances. And this gray area shows the variability in different seasons. But as you can see, as we are playing more and more games, concordance is getting closer to its maximum possible value, which is 435. And 435 is basically 30 choose 2. That's the maximum number of pairs of teams. So 435 means the two rankings match exactly. So there's not even a single pair of teams that, the two rankings disagree. And on the other hand, Euclidean distance, obviously the optimal and the best value is 0. And we are getting towards 0 as we are playing more games. And these blue lines are 4 hypothetical suspension days that we have tested in our experiments. Day number 80, 100, 120, 140. To see if we suspend games in day number 80, then how our solution for the remainder of the season can actually, how the solution methodology can be assessed via simulation. That, I'll show you the results for that. So hopefully the research question is clear. Please stop me if there are any questions. So anyway, in order to answer that question, we want to, first of all, uh, predict the result of the remaining games using the data that we have up until the day of suspension, and then using those predicted probability of the outcome of games, formulate a stochastic optimization problem to answer a question of which games should be included or excluded from the remainder of the season. So this was a unique problem, actually. We've had a lot of papers studying prediction sides, trying to propose lots of different models from machine learning models, Markov chain, a combination of, expert opinion and machine learning, etc. On the scheduling side, it was mostly scheduling from a blank slate or considering multiple criteria. Um, this fourth bullet point was somewhat relevant, and these papers try to draw a line in the middle of a mostly football, like soccer leagues, and then use the data up until that particular day to predict the final ranking based on strength of schedule. Uh, but again, even those papers didn't propose new games being played to improve the ranking, which what our paper did. Predictive model, we have a lot of um, features, overall team performance, basic team level statistics, some calculated team level statistics such as effective shooting percentage, etc. Player level statistics, so the same types of stats, but instead of team, we have those for individual players as well. 128 in total, and um, and actually something that we did that was very effective for our prediction problem uh, was using permutation importance, which basically might be familiar with that, right? So you take out one feature, you shuffle the values, and you try to see how much accuracy drops by removing that particular feature from the set, and then based on that accuracy drop, you have a ranking of features in terms of importance. The problem, of course, is a lot of features are correlated with each other. Now you can, so one solution is um, to do a clustering, which tries to find features that are close to each other, similar to each other, and then now you can select only a representative feature from each cluster, which hopefully you will alleviate that multicollinearity problem to a certain degree. And then once we do that, we actually saw that once we get to those clusters of features, we can find, a common theme in these clusters of features, as you can see. So these are ranked by the accuracy drop on the predictive side of things. Um, the first one is basically overall home team performance, style of play. The third cluster is mostly shooting. If you come down here, it's guest team shooting, etc. The last one is mostly assist, in terms of the home team assist and the away team assist, how much they are different, etc. Which was an interesting observation. Eventually, so we use this to try to estimate the result of the remaining games in terms of which team wins and which team loses. So basketball, there is no draw. It's a binary classification problem. So we want to um, predict let's say, the probability of home team win. So we use log loss, as you can see at the bottom, which is a proper scoring rule to find the best model. And according to that, logistic regression and some neural network based models actually performed better than others. We didn't look at accuracy to pick the best model um, because of its shortcomings. So why we have four columns of figures here. Each column here is for one hypothetical suspension day that I showed earlier. So as we suspend games later, um, there's less variability in the results. And these box plots are log loss or accuracy or AUC values from 14 different NBA seasons. So that's why we have a box plot and instead of a dot for each value. So yeah, so that was the predictive part. And then in terms of prescriptive part, so this is what we do in words. We want to minimize the dissimilarity measure, such as a Euclidean distance, and close the gap between shortened season and full season rankings, subject to a number of constraints. First of all, we want to accumulate the number of wins based on however number of wins that each team has had up until the suspension day, plus however many games wins each team has after the suspension day. Now, after the suspension day, obviously it's a random variable. We don't know exactly if the team wins or loses. Let's say Lakers host Celtics, and the model predicts zero point 0.7 probability of Lakers winning. So if you want to do a simulation, we generate random numbers. In 70% of the cases, home team wins, and 30% of the cases, guest team wins, and we do that for other games as well. So it's like a simulation-based optimization here. Um, so even if we uh, reduce the number of games, uh, we want to make sure that the number of home and away games are equal across different teams. So I will just skip the details of the mathematical notation because of the time. I will come back to this if necessary at the end. So here is the 5 different solution methodologies that we formulated. The first three is based on Euclidean distance, and that's a minimization objective function. And the last two is based on the concordance, which is maximization problem. Um, in terms of the concordance, we have a sample average approximation, which tries to make these decisions using as many scenarios as possible. And by scenario, I mean the different permutations of all of these game outcomes. So 259 games remaining in this particular instance. Each game has two possible outcomes. 2 to the power of 259 is the total number of scenarios that we have, which is massive. And it turns out that because as we increase the number of scenarios in our problem, our optimization problem becomes computationally more expensive. We can include a limited number of scenarios, in our case, only 50. But our hope is that relying on the predicted probabilities, we are selecting the most representative 50 scenarios out of those massive number of scenarios. But on the other hand, in terms of minimizing the Euclidean distance, um, if you focus on the Euclidean distance between shortened season ranking and full season ranking, we try to, so this is, uh, right. So in terms of minimizing the Euclidean distance between shortened season and full season rankings, we try to calculate the Euclidean distance between two similar variables, which is a good proxy for distance between rankings, but we had vector of win percentages instead. So if you rank teams based on their win percentages and note down their win percentages and rank numbers, um, the distance between rank numbers and the distance between win percentages are not exactly the same values, right? But one could actually approximate the other. So that's what we did. And by doing that, we actually saved a lot of binary variables. So it gave us an approximation, but turned out to be actually a very nice approximation. We eventually were able to write an equivalent deterministic formulation of that stochastic model. So in this problem, there's no expectation at all in this formulation. The expectation is represented by mean and standard deviation of Bernoulli distribution, which we assumed each game outcome is following. And overall, so these are some additional details that I'm going to skip here, sorry, for the sake of time. So if I want to show the computational experiments here, um, we had 14 NBA seasons. We excluded 2011 season because it was already a shortened season. It was, I think, there was player strike, and then the games were not, I think it was 50 or 60, 66 games. Anyway, so 14 NBA regular seasons. The second bullet point shows us as we increase the number of scenarios in the sample average approximation that the if the quality of the solution drops after 50 scenarios, so we cannot really solve beyond that. To test the performance of our solutions, we did Monte Carlo simulation using 10,000 generated game outcomes. And then we had a greedy algorithm, which assigned games according to the original schedule until a certain number of the number of games limit is met. This is not a ranking-based algorithm. This is simply a greedy algorithm. So, just skipping these computational results. So this was the main results based on the simulation. The ranking-based um, solutions are the pink one, which is the Euclidean distance-based solution methodology. And in terms of the metric itself, it's concordance. The higher, the better. And the best value is 435, but we do not get anywhere close to that. I mean, the maximum is in suspension day 140, expectedly so because again, we are suspending games later in the season. There's already very little basically variation in the results of the remaining games. But as we are suspending earlier in the season, there's a lot of variability in the outcomes. Each dot represents each season from 2004 till 2018. The greedies at the bottom, as you can see, some leagues are more competitive than others, which is not a surprise. And interestingly enough, if you track the individual seasons from one plot to the next, there are seasons that are competitive in the middle of the season, but not so much competitive later in the season, and everything is already determined who's top four, who's top eight, etc., etc. So, and then this was the um, assuming the pink one is the concordance if we play games, and the gray one if we do not play any more games and we stop on the day of suspension. As you can see, there's a massive difference in terms of concordance, which shows, there's certainly value in playing more and more games to reach a fairer ranking at the end, basically. So for the sake of time, I'll just stop here for this presentation. I'll just move to the next very quickly. This was also another one that we recently submitted to a journal. I wanted to just, in a few minutes, also talk about this. Or maybe I can stop if there are any questions from the previous one, and then I can uh, jump to the next. I don't know how we want.
Sure, yeah. Why don't we, there was one question from Oliver for the last part.
Yes, yes, Oliver.
Straightforward. So Oliver, if you want to,
Oh, sure. Well, I don't want to slow you down, but I mean, that was just a clarification question. In the beginning, you had this efficiency metric for players. It was called EFF.
Yes.
Uh, I just wanted to ask, is that a standard thing that, people in basketball analytics realize, or is that something that you developed?
No, it's I think John Hollinger, what was one of the main people that has introduced a few metrics. There is this player efficiency rating per, which is
Mhm.
talked about a lot in like ESPN, other networks. That I didn't use that because that's like a really a page-long formula that I didn't calculate at all. There are certain websites that show that. The formula that I used, which is actually very simple, but interestingly enough, provides the similar scale of values to per, and that's all the positive attributes minus negative ones. Positive meaning points, assists, rebounds, blocks, etc., minus turnovers and personal fouls divided by the games played. That's it. So that's what I used. And Wikipedia actually uses EFF to distinguish between per and this simple formula. That's what I used in the paper as well.
Thanks.
Yeah, no worries. Any other questions from the previous work? Right. Okay, so let me spend a few minutes on this one as well. NBA expansion, you guys in Vancouver should be familiar with this. Also, um, you know, so NBA started in 1946 with 11 teams, and then over the years, there's been expansion teams joining every few years. The last one, I think it was Charlotte Hornets in 2004. And since then, we've had 30 teams. There's a serious discussion around expansion, and there are certain teams from Canada. Vancouver is one of them. Montreal is another one um, among the list of candidates. And uh, so here's the list. I mean, this is the list that we came up with, reading lots of different articles and interviews with, NBA commissioner, other main um, basically decision makers in the league. Um, Two from Canada, as I said, Montreal um, and Vancouver, and also one from Mexico, Mexico City, because Mexico City already hosts a G League team as well, and Vancouver used to host an NBA team a while ago, and a few other American candidate cities. So we do not formulate the decision of which city should get an NBA team. That's obviously, I think, in our opinion, is really up for negotiation with ownership, and etc. But whenever this happens, there are other implications, especially in terms of the conferences and divisions, which, as you can imagine, instead of 30 teams, 15 team per conference, 5 team per division, we should have another format, either like 4 teams per division or 8 teams per division, which both of them actually have precedence in hockey and baseball and American football. But when that happens, there are some implications, and we want to study what happens and how we can actually comment on how we can realign these divisions, basically. And really, the one that we have lots of information and data that we can focus on is travel distance. The other ones are either we cannot get reliable or accurate data, or really difficult to basically merge with this analysis. So anyways, so the travel distance is the main factor that we focus on, plus some considerations in terms of the uh, revenue that I will talk about. In the current format, there are certain teams that are really disadvantaged because of which division or conference they belong to, such as Minnesota or Portland. They are traveling almost twice as much as, the team that is traveling, the team in the northeast of the country. So in terms of the travel distance, there's already a lot of discrepancy. Um, and I'll just move on to this plot here. So exact number of miles traveled by each NBA team obviously depends on the schedule of the league, because usually whenever a team visits other teams, there are multiple cities that they are visiting in a row. So there's a road trip. There's not like a single game trip back and forth. But uh, assuming that we can actually assume for each away game, the team leaves their home city, fly there, and come back, and then that happens for every 41 away game, which is obviously not what's happening in reality. We call that theory distance at the x-axis. And actual distance is what happens in terms of the actual miles traveled by teams in the past historical seasons. Uh, this graph shows us that we can actually assume a sort of a linear regression curve between actual and theory distance. Portland um, and Minnesota here traveling a lot in terms of the actual distance. So that's why we actually use this theory distance to formulate this division problem. Um, so very briefly, if I want to explain what we do here, we want to look at each of the new teams, how many miles they are traveling in the new format, and then the main decision is this Xij and Yij, which means if teams I and j should be in the same division or not, a binary decision variable, and then Yij if teams I and j should be in the same conference or not, again, binary decision. But this one, as you can see, looks at the overall distance traveled by all of the teams combined, tries to minimize that. Um, so But what solution methodology that we came up with was Nash bargaining solution, which looks tries to look at the travel distance as a utility function. And let's say all of these 30 teams have a say, have a utility, and we want to make everybody happy. So we look at the dot product of all of these utility functions by all the NBA teams, and we define this utility as how much we are increasing their travel distance by adding these new expansion teams. So that's a nonlinear term. We take a logarithm and we do some cutting plane here to basically try to solve that using piecewise linear functions. And once we do that, um, I'll just get to the results here. Once we do that, we'll see that basically there are some alternatives in terms of the one on the right is the current format, 6 divisions. The one on the left is a 8 division scenario. As you can see, there's a lot of moving parts in terms of which division, including which teams, etc. And we can also look at other scenarios such as 8 78 7 sorry 72 game season instead of 82 game season, which is in the discussion. We can also look at 8 teams per division, how much travel distance differs between the multiple teams. But basically, this gives us a nice decision support tool to focus on the basically divisions and how we can, once the 2 teams that we want to add to the NBA, which apparently NBA wants to charge each expansion team like I don't know, $5 or $7 billion, something like that, to join the league. Once that happens, then the question of how we can change the divisions, how we can realign divisions and conferences. So this study basically focuses on that second problem. Um, I have a few more slides, but I will stop here because I don't want to run over time. I didn't talk about cricket, etc., but I, I don't know if anybody is interested. We can maybe talk offline or over email. So yeah, I will stop here.
Great. Thanks very much, Ali. We'll open up the floor to questions. And maybe I'll just get started. So if you have a question, please just raise your hand and I'll call on you to ask it. I was curious, you talk about expansion, and yeah, I think we do here in Vancouver definitely know and suffering from the Grizzlies experience. But can you comment on, or have you looked into expansion draft fairness at all? This is one thing. So I'm more of an NHL fan, and my team was an expansion team in 1992, and I recall at the time that how bad, that or how unfair I feel like the expansion draft was relative to, for example, to more modern expansion teams like Las Vegas in particular. Like,
Mhm.
how do you come out of an expansion draft and be a Stanley Cup contender 2 years later? I
Mhm.
mean, that to me was extremely unfair. So I'm wondering if you've looked into that problem at all.
No, Dave, I can imagine how interesting of a problem or difficult of a problem it could be. And I don't know how similar it is to the NBA expansion draft. So in the NBA, from what I have studied, is teams retain certain number of players, and
Yeah.
then yeah, so and then you in the case of NBA, the expansion teams really were struggling for so many years. But no, I haven't looked at it to be honest. I have actually the next slides that I didn't get to, which is a joint work with one of my MSc students, is on the Indian Premier League draft, which is, I don't know, might be actually a little bit similar to the NHL or NBA expansion draft in the sense that there's a lottery. I don't know, this could actually be a solution, but NBA teams obviously won't be happy with this. There's a lottery each year. As a team, you get to retain certain number of players, and then let's say, I don't know, 6 or 8, and then everybody else enters this huge pool of players, and teams are naming their prices to form their roster. That happens every year, and every 3 year there's a mega auction, which means there you don't even get to retain any players. Everybody enters this massive auction, and there's a huge overhaul of players. So it's like this crazy format that you see teams completely revamping their structure and their roster every year. Um, but this is as far as I've gotten with master students. I haven't looked at expansion draft at all, unfortunately.
So sorry, this is like completely foreign to me.
Yeah.
I don't watch cricket, but you're literally like you have to give up a certain number of players every year, and is the
Yes.
lottery, is it a weighted, like do they, based on your ranking get
Sorry. No. Sorry. I misspoke. I should say auction, not lottery. I
okay,
got
auction?
confused
Yeah,
with NBA. Yeah, not lottery. Auction. There's auction.
I see. So if you want to poach a player from another team, you have to then pay them a certain amount of money.
Yes.
Okay.
Yes. And there are certain rules in terms of the number of Indians, number of international students you can recruit, etc., etc. So you have to follow those as well. So in this study, which we sent to MIT Sloan Conference, um, so as a team, you first try to predict the value of every player, and you look at which players you have retained, which positions are still you need to fill out with good players, and then you do this optimization every time that a move happens, and you need to update your information in terms of available players, and then you try to do that. And the objective function is trying to make the playoffs or maximize the chances of making the playoffs, something like that.
Hmm.
But yeah, it's a very different format, and obviously they're uh, you know not gonna happen in
Yeah.
American or North American leagues.
I mean, what are some of the major strengths and limitations of that approach?
Um, Strength, I think a lot more. So it brings a lot of teams look a lot more similar to each other than other leagues, that you can become a powerhouse and you can stay like a dynasty for so many years. It's basically not possible here in this league because
Hmm.
every 3 years there's a mega auction, which means everybody leaves your team. You have to build from scratch. Obviously, there's coach, there's culture. Um, I don't even know players have a say here or not. I don't know, to be honest. Um, But in that sense, there's an advantage, disadvantage for teams. If you're been playing like in a league like in NHL or NBA, there's no way you'd be happy with this, right? So because you want consistency, and there's no consistency here.
Right. Um, and then does it like, do you have a limited amount of, like, is there a cap on how much money you can spend in the auction?
Yes, there's a minimum and maximum, just like NBA. There's a minimum and maximum that you should spend, you can spend, yeah,
I see.
something like that.
Very interesting.
Yeah.
Does anyone else have any questions?
Yeah, so I'll just go to the last slide here.
Okay. Well, if there's
Oh,
no,
no, no, I can.
oh, sorry,
Can I say something?
go ahead.
Yes.
Yeah, so thank you for the talk.
Hmm.
Maybe this is a comment. So I think the general program here is to say, oh, we're going to define properties, desirable properties of a schedule, and then we run optimization to find schedules that meet that. And I think that's a cool research program. Sounds useful and challenging. Um, I guess I got, I do optimization too. I got, many questions about the details, but there's something I didn't quite, or I wanted to, maybe two comments. One is understanding. So when you were doing the win percentages and then you said, oh, I'm going to compare the shortened season with the full season,
Hmm.
um, the picture I got is that you're holding out the games from the full season and you're sort of treating that as a holdout set. And then when you optimize, you try to minimize the distance between the ground truth from the whole season and the guess that comes from the shortened season. Is that the methodology at a high level?
No, no.
Mm,
So the what happens is the guess appears in both full season and shortened season, right?
mm,
Because ground truth, we don't know it. We can just we can only rely on those predicted probabilities to generate scenarios.
mm-hmm,
So let's say you have 300 games remaining and you want to select, let's say there are 200 games remaining and you want to select 100.
mm-hmm,
So for those 200 games, we can only come up with the predicted probability in terms of what's the outcome.
mm-hmm,
And for for the full season, we just enumerate the wins for each team based on each scenario, one or zero, right? And then for the shortened season, we enumerate these outcomes, but there's also this decision variable X, which is looks at each game whether we include or exclude. So even if a game counts as a win for a certain team, if we do not include that in the shortened season, obviously we don't count that. But that random variable, which is based on the outcome of the remaining games, appear in both full season and shortened season, uh, ranking. So
yeah. Okay, I may have to. I mean, I guess I feel like I just have a really basic question, and it's so basic that you're probably like,
okay,
"Oh my
I
God,
make
how
it
can he not get
complicated.
this?" Like you said, there's no ground truth, right? So if the
Yes,
NBA season, so you're optimizing something, right?
yes.
And how do you know that you've optimized the right thing? If I just said, okay, every match ends in a tie,
Mhm.
there must be some piece of your system that's saying that's not a good metric, that's not a good result. I guess
Mhm.
yeah, I feel like there must be some ground truth somewhere that you're using, or some way in which you know that the outcome of your
Yeah,
simulation is better.
yeah.
Mm.
So okay, so if once so we were looking at 2019-20 season, but we were using 24 till 2004 till 2018 seasons as test bed, right? And for
Uh-huh.
those seasons, because we used a hypothetical suspension day,
Yeah.
we had actually ground truth, right?
Right.
We
Okay.
did know the outcome of the games
Okay.
post
Right.
hypothetical suspension day.
Okay.
We could do a back test, which we did actually. You can see it in the paper as well. We could do a back test,
Yeah.
saying, okay, so we are selecting these games, and then we are taking out these other games, and then the full season, just let's just look at the outcomes of the games that already happened a year from now, a year ago or 2 years ago,
Right.
whatever, and then compare them.
Yep.
We have that, and obviously that the back test is only one scenario, right? So instead of like
Mhm.
10,000 simulated scenarios, it's the actual scenario that happened in reality.
Mhm.
We actually saw some favorable results from that, even though not as significant as simulation in certain cases. But backtest also helped us to show that using a ranking-based algorithm is actually makes sense um, compared to a greedy algorithm or compared to a scenario where you do not play any more games.
Okay. So I think I
Yeah,
got
I
that.
think
And
you're
then,
referring to
yeah.
backtest probably as like,
Yeah, yeah, something like a back
yeah,
test. Yeah, yeah,
okay,
it makes sense.
yeah, yeah,
Uh, and then I guess another high level question. So I believe that the way you set that up when you kind of impute the results of the missing games, right? You basically simulate the outcomes, right? You say, oh, I'm
yes,
going to have these 20 games. I'm going to predict who's going to win.
yes,
And that's wonderfully ambitious. That's great.
yeah,
We had Jonathan Waller from the Canucks came once to us, and he said, "Oh, I'm so jealous. In basketball, they can simulate entire seasons, and in hockey, that's so hard." Anyway, but the my question is, you can also frame it as another problem, which is just predict the final ranking.
Yes.
right? And
Yeah.
yeah, I think you cited the work Van Haren and Davis. So generally speaking, if all you want at the end of the day is the final ranking, that's a significantly easier problem than, right, predicting any match outcome, let alone like sets of match outcomes. So
Yes.
I feel like you kind of, yeah, you kind of set it up to be very kind of, first you solve a very ambitious and hard problem,
Hmm.
and in order to solve what's actually an easier problem, so I guess I could say, why not just directly try to predict the final ranking without,
We
going.
can, yeah, we can, but we have some discussion in the paper and more in the review process that didn't make it to the final draft that there's still room for improvement in terms of the gap between that full season and shortened season ranking,
Hmm.
because you can imagine a scenario where certain teams have had really bad schedules and they were hoping to, get a breathing room at the end of the season to have some easier schedule, make up some ground, start winning some games, etc. If like those extreme scenarios happen, your predictive model should be really advanced to pick up on those like strength of schedule, um, you know, uh, considerations to be able to actually anticipate the performance of teams in the remainder of the season. If the schedule was difficult, okay, so this team, we are predicting that this team will start winning some games. Okay, so let's just predict that instead of actually letting them play the game. Um, yeah, so the algorithms that these papers that I cited used were actually very simple. I did implement them, and at least for those particular papers, the results weren't that great. Which uh, and I did that I think before my first submission, which got me even more excited about the idea of playing more games. Otherwise, yeah, I agree. So if there is a method that can predict without letting teams play more games, okay, so let's just predict them, especially like in COVID, lots of, you know, concerns around contracting virus, and they really wanted to minimize the number of games played, etc. Yeah.
Okay.
Otherwise, in general, playing more games is always, profitable, right? NBA wants to maximize the number of games played.
Okay, yeah, very interesting. Thank you. I asked too much. Dave was probably saying, Oliver, shut up, it's past time. So thank you for answering. Yeah, it was
Thank you,
helpful.
Oliver.
Definitely false accusations. Good job, Oliver. I will, however, on that note, just shut off the recording. So thank you again, Dr. Hassanzadeh, for an
Yeah,
interesting talk and for
my
answering
pleasure.
questions.